Long time no see, and today we continue our work on math statistics and theory of probability. I remind you that the very last our topic was dedicated to the binomial distribution. Binomial distribution. Sometimes I use a term binary distribution. I don't know why I'm used to using this term because it's wrong. We are talking about binomial distribution. And I remind you, what does it mean about binomial distribution? So we have just two outcomes. Or we can talk about success or failure for these outcomes. Success or failure. And examples. It's very useful and very important distribution, and because there are a lot of examples in real life. For example, the treated patient can die or can survive after surgery, for example. After surgery. Right. What I mean. Treated patient. Treated patient and surgery, for example, can die or can survive. So we have just two outcomes. There is no any other possibility. Okay. For example, if we are working with t term here, and here, for example, we have a traffic light here. I denote them like using green and red inks to denote the traffic lights. So any car can turn to the left or can turn to the right. Any car. There are, that the third possibility, it can perform U-turn here. But for example, if U-turn is prohibited, it has just two opportunities here. So for example, we have a coin, and it flips or turns up. Head on tails. We have just two opportunities. If it is fair coin, it gives head. It turns up head with probability 0.5 and 0.5 here for tails. Treated patients can die or survive. I very hope that they can survive with probability much more than probability to die or die. For example, these probabilities. Okay, so we defined during our previous lecture that if we have n is a number of trials, and R is a number of successes. So the probability to have R number among n trials, I put like Rn here, equal n factorial over r factorial over n minus r factorial times p raised to power r and q raised to power n minus r. And usually q is equal 1 minus p. Okay. By the way, p is a probability to get a success outcome, this successful outcome, successful outcome. Okay, so I've got a question: what does it mean success or trial? And trial is an experiment. For example, if you are tossing down a fair coin, this is the experiment or trial. And success, for example, I pick out success as a head side of the coin. For example, for treated patient, I think it's doubtfully we doubtfully can say that success is death. And this case then patient survives is a success here. Here it's your choice, because maybe it's very important to you that any car turns to the left side, and you can consider the left side turning as a success. But maybe you are very keen on the right side direction, because I don't know, maybe here you have a dead end or something else, and that's why you consider this turning to the right side as a failure, for example. Okay. For example, if you check some item, the success to get the "Hi guy, how are you?" That's my boy, my cat, Tomcat. He's a boy. The success to get it's your choice here. So sometimes it's very obvious thing, and it's a kind of logical thing. It's clear on the hand that success here is when people survive. Here it's just your choice. Maybe you consider head as a success because it was your bet, or maybe you consider here right side turning. So it's your way. So I remind you here a piece of our previous lecture, the probability function and R. Here P is a probability or success event. Q usually is 1 minus P, because here we have it is 1 minus P because we have to satisfy the axioms of probabilities. And R, and number of trials, and R, number of successes, So moreover, they calculated the mu, which is expected value of R, or we are set it math expectance, or we say it mean value or average value, and it's equal NP. And we calculated the variance for this binomial distribution. And recalculated dispersion or variance or the distribution variance. Here math expectance or expected value or and here we have variance. And it is NPQ. What else do we have here? And standard deviation, it is sigma or square root of NPQ, or these distribution. So you have as your home assignment a job to make the math distribution function or probability math function, and to plot the probability distribution functions for all these binomial distribution. And I make, to enable your work, to facilitate your work, I want to make here an example. Okay. For example, you have a binomial distribution. You have n equal 10 trials, number of trials 10, number of trials 10. And the probability of success is, for example, I calculated, and that's why I want to check which number. 0.15. 0.15. For example, you have very unfair coin, and I don't know how they did it, but this coin gives heads with probability 0.15. If it were a fair coin, it would give about it would have the probability to show head side 0.5. You understand it? But here we have very unfair coin, and it has probability 0.15. So we want to define a plot the probability distribution of probability mass function and probability distribution function. Two of them. Okay, let's start from the probability mass function. Probability mass function sends a random variable r to its probability. To its value or probability. And now we have to define all run r to the all number of successes and calculate the probability of these numbers. So we have r can be, if we have n trials, r can be 0, so no one of 10 trials gives success or head side, for example. Only one. It's possible you can choose down a coin and you can have 10 times in a row and you just have one time ahead. It can be even if you chose down the fair coin. So the same thing is about unfair. 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 possibilities, 10 possible results of our trial. Okay, now we have to calculate the probability. Probability. Okay, I use this formula for calculation. For example, if n equals 10 and r equals 0, this formula gives me 10, r equals 0, 10 factorials, n minus 10 minus 0 factorial, 0 factorial here, 0.15 raised to power r, it is 0, and q you know that q is 1 minus p, 1 minus 0.15, and it gives me it's power 10 minus 0. 10 minus 0 minus 0 is, consequently I have 10 factorial over 10 minus 0. 10 factorial, O factorial gives 1, 0.15, 0.15 raised to power 0 gives 1, and 1 minus 0.15, it is 0.85 raised to power 10. I can cancel 10 and 10 factorials, and it is 1, 1 times 1, 1, and it just 0.85 raised to power 10. You can use your calculator, but I calculated before using Excel, and it is 0.197. I use the 0.197. Okay. Clear. For example, the next one, when r equal 1, so it means that you chose 10 times in a row, and you have a head side, the head side only once. So we can use the same formula here, but instead of 0, r equal here 1. And I have here 10 factorials over 10 minus 1. 1 factorial here. 0.15 raised to power 1. 1 minus 0.15 equal raised to power 10 minus 1. And you have here the result is 10 factorial over 9 factorial, 1 factorial, 0.15 times raised to power 9. Okay, so we have here, I can cancel this 9 factorial. Here I have 9 factorial times 10, I have 10, these numbers, but I'm very lucky. I use the Excel program and I can write down 0.347. 0.347. Okay. So now I think it's clear that we can have all of these R put here and recalculate probability of each event of our for our job. We can have 2 heads, 3 heads, or something when we are tossing. I want to write them down here. 276. Так, 0. 0.13, 0.040, 0. That's it. And here we have very little numbers. For example, I have 3 times 10 raised to power minus 7, so it has 7 zeros after point, and 5.8 times 10 raised to power 9 minus 9. So this number has 9 zeros after point. So we are ready to make to plot probability mass function graph. By the way, you can use Excel and you can check if you calculated everything correctly. You can add all of them, these numbers, and if you calculated everything good, this summation is equal 1. Summation of these probabilities equal 1. Now we are ready to make a plot. To plot the graph of this. Now they are ready to make a plot, to plot a graph, to plot a graph of this function. So I can clean everything here. Okay, x is x, and so we have to make xy rectangular system of coordinates. X, oh r, I'm sorry, x is x I associated with r, number of successes, and x is y I associated with probability function P. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 points. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I do know then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And along axis P, I have to cut the beans with lengths according to these P numbers. So the maximum is 0.3. So maybe this one is 0.4. Okay, this is 0.1, 0.2, 0.3. This is the new scale. And now I have to make these, to cut beans, these lengths, according to P. So 0.19, it's about a little bit less than 0.2, I can put it here. So this is one, this one P number. 0.3447, it's about middle point between 0.3 and it is here. So this bean has length here. 0.278, it's a little bit less than 3. So it's here somewhere. 0.130, something a little bit more than 0.1. Okay. 0.04, it's very close to the 0 because it's less than decimal part. And the other one, they are getting more close and closer to the axis R, so I can make them very schematically. So you can see here the probability mass function for binomial distribution when P equal 0.15 and we have n equal 10 number of trials. Here we have very schematically probability mass function. Okay.